You're rushing through a morning shift, and the ingredients aren't cooperating. The bread you left out is spoiling, the heavy-duty cleaner won't lift the grease, and your instant coffee is just a sluggish, muddy mess at the bottom of the cup. These frustrations happen every day in busy shops like Kuya Ben's Kapehan on the shores of Lake Cebu. On the surface, it looks like a run of bad luck with the supplies. When a recipe fails or a cleaner doesn't work, we tend to treat the process like guesswork. We assume that if we just stir harder or wait longer, the ingredients will eventually do what they're told. But to fix these macro-world problems, we have to look at the micro-world. Brewing coffee or mixing soap isn't just a chore. It's an exercise in managing a chaotic environment of invisible, moving particles. The way that coffee dissolves, that bread spoils, and that soap cleans is dictated by a specific physical framework, collision theory. A chemical reaction is a physical event. For two substances to interact, their microscopic particles must literally crash into one another. But not every bump causes a change. First, the particles need enough energy. They must hit each other with enough brute force to shatter their old bonds and form new ones. Second, they need the correct direction. Even with high energy, if the particles strike at an off-center angle, like a missed high five, the collision fails and they drift away unchanged. Because chemical reactions are mechanical collisions, we can adjust specific dials in our environment to make these impacts happen more frequently and with more power. Our first point of control is temperature. Heat is movement energy. By cranking up the heat of your water, you force the coffee particles to race around, causing the high-speed, high-energy collisions needed to dissolve the powder. The same logic explains why food stays fresh in the refrigerator. Cooling removes that energy, slowing the particles to a crawl. They can't hit each other hard enough to trigger the reactions that lead to spoilage. Our second point of control is concentration. If you want a stronger brew, you add more powder to the same volume of water. By packing the space with more particles, you make frequent impacts a mathematical certainty. You can increase this frequency even further through surface area. A solid sugar cube only lets water strike its outer edges. Crushing that cube into powder exposes millions of tiny new surfaces, giving the water particles vastly more targets to hit at the same time. By adjusting heat and physical crowding, we can dictate exactly how often and how hard these microscopic building blocks interact. Sometimes you cannot use intense heat to force a reaction, like when you are waiting for bread dough to rise. Too much heat would simply kill the yeast. This chart shows the energy barrier a reaction has to overcome, represented by this tall hill. A catalyst, like yeast, speeds up the process by providing an easier path, this much smaller hill, which requires far less starting energy. Even with the right energy and a clear path, a reaction won't finish correctly unless you provide the ingredients in the correct proportions. This is stoichiometry. Chemists use a counting unit called a mole to track atoms. A balanced chemical equation is an exact mathematical recipe. If a cleaner requires 2 moles of chemical A for every 1 mole of chemical B, any deviation from that ratio leaves you with wasted ingredients or a failed reaction. The math is unforgiving. You can force the particles to collide with perfect energy, but if the ratios are unbalanced, the chemistry simply stops. Back in the kitchen, the morning rush is now under control. The coffee dissolves instantly, the cleaners work as intended, and the bread dough is expanding exactly on schedule. The shop is no longer a place of guesswork. By understanding the microscopic world, you've turned the counter into a predictable, functional laboratory. By managing the dials of temperature, surface area, catalysts, and stoichiometry, you are actively directing the behavior of every particle in the room. Whether you are an industrial chemist or a barista at Lake Cebu, understanding the mechanics of a collision turns a series of everyday frustrations into a manageable, repeatable process.